Okay, in this video I'm going to continue on with my tutorial series on thermodynamics and statistical mechanics. This is video number 44 and I'm going to talk about the phase transformation for a pure substance. My website is universityphysicstutorials.com. The previous videos to this are as follows. Number 43 I discussed the chemical potential of an ideal gas, and number 42 I showed that the Gibbs free energy per particle is equal to the chemical potential. So let's just do one or two definitions. A graph of the, and I have to draw this in another color, we'll say green, of the equilibrium phases as a function of temperature and pressure is called a phase diagram. Okay, I'm sure you know that, but it's important that we come up with that particular definition. Next, the lines on a phase diagram represent the conditions under which two phases can exist together in equilibrium. Now this is an important phase, or phrase. The reason it's important, it means, for example, that you can have solids and liquids together, solids and gases and liquids together. And I suppose you can actually, no, I can't really have solids and gases together, but it means that you can have both phases present at the same time, which is a bit of a strange one. And finally, the vapor pressure. The vapor pressure is the pressure at which a gas can coexist with its solid or liquid phase. Now you might say, hold up a second, wasn't I talking about saying that you couldn't have solids and gases living together? But you can, but it's under particular conditions. Solids with a solid or liquid phase. And I'm going to discuss actually when it might be, something might be coexisting between its solid and gas phase. Okay, so there are three definitions which we need in order to continue. I'm sure you've seen them, but this is one actually which I keep forgetting. I have to keep going back to the definition for some reason. It never sticks in my head. So if we plot, let's look at a particular molecule. Let's look at the CO2 molecule, right? CO2, like that. So if we plot CO2 on its phase diagram, so we're plotting it as a function of both pressure and temperature. So temperature is on the y, and pressure is on the y, and temperature is on the x, like that. And you just have to believe me, okay? So it's pretty straightforward, but you just have to, I suppose, you have to believe me here. So it looks something like this, and it branches out here like that. And it does something like this. Like I said, something like that. It doesn't necessarily, it's not perfect. I suppose it curves better here, doesn't it? Yeah. Okay, I think that's a better definition. So on the green, so this area here is where it is a solid. This area here is where it is a liquid. And this area, and all to the right of that, is where it is a gas. Okay, so I said the lines on a phase diagram represent the equilibrium phases. So that means, for example, if you somehow could vary the pressure and the temperature so that you'd follow this line up, it means that from here to here your CO2 would be in equilibrium between its solid and gas phase, and from here to here between its solid and liquid phase. So you'd have both liquid, for example, from here to here, you'd have both liquid and gas existing together in the same point at the same time. From here to here, you'd have both the solid and the gas, existing together at the same time. And if you then followed it from here up to here, you'd have both the liquid and the gas phase existing together at the same time. Now let's just put in some numbers. So this is 73.8. We're talking we're talking in bar, by the way, so I'm not going to write it in, but the pressure is in bar, and the temperature, so we have 0.56. Okay, this is in degrees, and let's say we have, I don't know, let's say we have 31. We have 31 degrees here, like that. Okay, so this is temperature in degrees Celsius, pressure in bar. Now let's look at atmospheric pressure. Okay, so let's say atmospheric pressure is about 5.2 bar. Okay, so if we look at, this is atmospheric pressure here. So if you step outside your room and you had CO2, that's the pressure at which you'd have CO2. So at atmospheric pressure, increasing the temperature, so if you increase the temperature, in other words, follow on the horizontal line I've drawn here. If you increase the temperature, you cause a transition from the solid to the gas phase, a direct transition from the solid to the gas phase, and we know what this is. It's called sublimation. So, for example, when you're in the nightclub and they talk about, they have the CO2, they bring out the CO2 and just this white smoke, or I suppose you could call it. But really, what they do is they bring it in they bring it out as a solid, and they release it into the atmosphere. So it's atmospheric pressure. It's atmospheric pressure, but the temperature is obviously going to be room temperature, and immediately the gas or the solid will sublime to its gas phase. Okay, so that's I think an interesting example. So where do we go from here? Well, we need to look at the liquid gas boundary. So the liquid gas boundary. So the liquid gas boundary has a positive slope. Okay, so if you remember a moment ago, our liquid gas boundary, it looked like this from here to here. It looked like that. So it has a positive slope, and that's important, believe it or not, because what it means is as follows. It means that if you raise the temperature, you require more pressure. You require more pressure to keep it as a liquid. Okay, I'm going to go back to the graph in a minute, but it's important here that on the liquid gas phase boundary, if you raise the temperature, you require more pressure to keep whatever you have as a liquid. But the problem here is that as you increase the pressure, okay, as you increase the pressure, you increase the density. You increase the density. So the point here is that the distinction between your liquid and gas ceases to exist, or we'll say it gets less and less, but it does cease to exist. So there's less distinction between your liquid and your gas phase, PHASE, and it actually ceases to exist at the critical point. So the point here is that at the critical point, the pressure and therefore the density of your substance is so much that there is no distinction between its liquid and gas phase. So using, we'll say, what we had a moment ago, we had CO2. Okay, so this is pressure on the Y, temperature of course on the X, so it looks something like this. Okay, it looks something like this, and we're talking about from here to here. So if you noted, right, so this is temperature and this is pressure. So let's say we're on the liquid gas phase line. So say we're here, right? And we want to increase the temperature. There's the gas and there's the liquid. So if we increase the temperature, it stops being a liquid and a gas and just becomes a gas, full stop. But if we increase the pressure, we go to here, for example, and we're still on the liquid gas phase line, and we have both the liquid and the gas coexisting together. But as we keep doing it, we keep doing it, we keep doing it, we keep doing it, there comes a point which I'm going to mark here, and we're going to call this the critical point. And after this, there is no more a liquid-gas phase line, it just stops. At the critical point it stops, and the reason is because there is no distinction between the liquid and the gas phase. Okay, and that's what we call the critical point. So next, okay, solids and liquids have no critical point. And this is because the solid has an ordered structure and liquid has a random arrangement. Next, the next piece of information I'd like to give you is that helium is the only known element. Helium is the only known element which remains a liquid at 0 Kelvin. It remains a liquid, we'll say approximately 0 Kelvin, because we still can't get to 0 Kelvin, the laws of thermodynamics do not allow, but we do get awfully close, that's for sure. Now, changing other properties such as the magnetic field such as the magnetic field full stop, I suppose, can cause a phase change. So, like, it's not just temperature and pressure. We can also get other phases, and that's an important thing, because I suppose sometimes in physics you just kind of forget that there can be other phases. Like you can have Bose-Einstein condensates, for example, and that's a new phase of matter. You can have superconductivity, which I'm going to show you now, is a new phase of matter. So let's say if you plot the magnetic field, which we're going to give the placeholder B, you plot B versus temperature. So some substances have we'll say the following behavior, that in this area which I'm going to shade, it becomes superconducting, and that means it has no resistance, and we call that is a new phase of matter. So this time we're plotting a B versus T graph. Alright, so it's not just pressure and temperature, sometimes there are other variables which we might plot. And let's once again plot B versus T. And this time I'm going to do it for a ferromagnet, okay? So for a ferromagnet, and I'm going to use my blue, so let's say from here, so it might be magnetized up, and this might be magnetized down. Now you don't need to know what magnetized up and magnetized down means. You just need to accept that a piece of material can have a property of being magnetized up and can have a property of being magnetized down. But at the critical temperature, it ceases to have this, and it's neither magnetized up nor magnetized down, and it's not magnetized, full stop. That's what a ferromagnet is. So we see that there are other phases other than those caused by pressure and temperature changes. I'm going to try and give an example. Let's talk about carbon. Okay, so carbon. We talk about carbon. Now, can you name some forms of carbon that we know? We know graphite. Graphite is a form of carbon, but there's also another one I want to talk about, diamond. You might say, what is the difference between graphite and diamond? Well, the answer really is their cell structure. That the cell structure of diamond is different than that cell structure of graphite, even though they're both made of carbon atoms. Alright, so that's the difference. But why are they different is the question. At what point does graphite become diamond or diamond become graphite? Or under what conditions is one stable and one not stable? Now the reason you have graphite and diamond, both carbon, but you have two different cell structures causing two different materials, is because one is more stable under particular conditions. P-R-T-I-C-U-L-A-R, particular conditions. Okay, so I hope you can see that. You sure can. So at particular conditions, graphite might be stable, but at other conditions, diamond might be stable, and that's why you have graphite and diamond. But go back to my video where we talked about the relationship between the Gibbs free energy and equilibrium, or free energy and equilibrium. What we found is we know that the world or the universe wants to increase its entropy. So it's equivalent to increasing the universe's entropy if you minimize a system's Gibbs free energy or you minimize a system's Helmholtz free energy. That is something I showed in the video maybe 5 or 6 videos back. Alright? It's equivalent to doing that. So let's look at the Gibbs free energies of carbon and the Gibbs free, or excuse me, of graphite and diamond. So we'll find that the Gibbs free energy of diamond is greater in general than the Gibbs free energy of graphite. But this is the minimum of the two. So usually it is the case that graphite is the more stable because it has the minimized Gibbs free energy or the maximized entropy. Alright, so that's why the graphite is usually the more stable. So if we look then at the thermodynamic identity for the Gibbs free energy, we know that dG is minus S dt plus V dP plus mu dN. Alright, so if we look here, we see that dG dP is equal to V. That's something I've used in the past when I was getting the chemical potential for an ideal gas. So now we know how the Gibbs free energy changes with pressure. So whichever of our two, either namely graphite or carbon, has the largest volume, it will have the larger Gibbs free energy at high pressures. And if it's got a larger Gibbs free energy, well then it is going to be less stable, or excuse me, it's going to be less stable, of course, less stable. So I'm going to plot pressure in kilobars, and we're going to plot the Gibbs free energy, of course, in joules. So let's say that this here is diamond, and this here is graphite. That's graphite. So in the region I'm going to shade in green, diamond is more stable than graphite. I'm going to do that actually with a small g to distinguish it from the Gibbs free energy. So in the region here being shaded in green, diamond is actually more stable than graphite, and that's because its Gibbs free energy is less than that of graphite. Whereas in the region I'm shading in blue, it is graphite which has the more stable parameters. Okay, and that's because the Gibbs free energy of one is smaller than the Gibbs free energy of the other. But you have to remember the pressures of what we're looking at. We'll say the critical point here is at about 15 kilobars. Kilobar. And that's a pretty large pressure. So the whole point is at normal pressures, which you and I are used to, we don't have 15 kilobars, and as a result, graphite is more stable than diamond. So by the way, if you were to throw your diamonds into the fire, you can expect them pretty quickly to become graphite because the temperature is temperature and pressure. Using the ideal gas law. All right. So yeah, I think that's all I've got to say about that. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and please visit universityphysicstutorials.com.